3 o'clock. Let's get started. Welcome everyone.
Okay. Okay, so if you're here for my class, there's a sign-up sheet here, so don't forget to sign up at some point. If you have questions, you can ask questions as he's going through, and there will be time for questions at the end as well. So, whenever you're ready.
Thank you, Professor. Hello everyone again. For those of you who don't know me, I'm another triplet. I'm going to talk a little bit about my CS298 project today, and the title kind of spoils it. We're going to be talking about bot detection, and especially on social media, using a particular technique called a dropout gap. So let's start with a little bit about the actual problem. So whether you're on social media or not, whether you're on Instagram or Facebook or Reddit or whatever social media you want, it affects us all indirectly or directly. You might notice a lot of news articles usually mention a tweet, or X now, as people would say it, when they talk about very famous figures like the President of the United States when talking about very important issues. So we can't deny that social media is now a part of our lives, whether we like it or not. Unfortunately, there's more than just humans on these social networks, and the slides might tell you they're actually bots or computer algorithms on the social network. And it is a problem. But before we talk about that, let's define what I mean when I talk about bot accounts. So for our definition, there's 3 important things to remember. The first thing that we want to know is it's a computer algorithm that wants to mimic humans, so they're not saying up front that they're a bot. The second thing we want to remember is that they produce content. So on a platform like YouTube, this could be video content. On a platform like Reddit, this could be text content or any other sort of content. But they interact with users through this content. And the users don't have to necessarily be human users. There's also possibilities where we have bot accounts interacting with other bot accounts. So now that we know what a bot account is, now I can tell you that bot accounts can be used for spreading misinformation or committing cyber crimes. There are bot accounts that are not malicious. For example, there are some bots which try to summarize news articles or try to provide some sort of utility. But there's also accounts that try and spread misinformation. They try and influence elections or even aid phishing, for example. That is the sort of bots that we want to detect. So the problem is twofold. The first problem, obviously, is how can we detect these bots? And that's pretty straightforward. There's also a second problem, and this is a problem with all of security, I could say. Let's say we come up with a model to detect bots. Currently, well, the creators of the bots are not going to rest on their laurels. They're going to figure out ways to evade the current state-of-the-art methods to detect bots. So our problem statement is also about how can we predict how these bots might evolve to fool our current models. And with that said, and the problem set, let's start talking about a little bit more about the background of this research problem. So the first thing we want to know is the technique that I used for bot detection. It's called generative adversarial networks. The interesting thing about this machine learning technique is that it actually consists of 2 models at odds with each other. And the 2 models are called the discriminator and the generator. You can think about it this way. Let's say we're trying to create very convincing fakes of famous paintings. In this case, the person generating the fakes would actually be the generator. And the person who's trying to figure out whether a painting is a fake that the generator has made or is actually a real painting would be the discriminator. The interesting thing to remember here is that the loss function for these 2 models is kind of intertwined. Only one model can win during training. So, of course, if the discriminator figures out that this is some output that's produced by the generator, then the discriminator gets rewarded. It's successfully figured out that it was generated output. And so on and so on, and vice versa applies. So if the generator is successfully able to fool the discriminator, then the discriminator is penalized, the generator is rewarded. Now let's talk about mode collapse. This is a specific problem with generative adversarial networks, or GANs. So what happens during GAN training sometimes, specifically with a generator, is even if your input training data looks something like this on the left, you can see there's 3 different kinds of shapes and 3 different types of colors. The generator will somehow only produce a very small subset of the actual training set. So even though we see 3 different shapes and 3 different colors on the left, we're only seeing green squares on the right. And the formal way to describe this problem is called mode collapse. You'll see why I mentioned this in just a few slides. Onto the data set. So we use a data set called ngTAP. It has about 400,000 users and about 40 million associated tweets in 54 different languages, so it's not just English. The interesting story about this data set is that out of the 400,000, only about 10,000 are labeled users. So we only have labels for about 10,000 users, whether they're bots or human. And of course, there's a breakdown of how many humans and bots there are in that 10,000. For this data set, obviously, we want to extract tweet features, and there are 54 languages, so we can't just use BERT. BERT was developed only for English. So we use a variant called LADSC, which is basically a multilingual flavor of BERT to extract tweet features. And in total, we end up with a 788. Of course, we have to do some sort of scaling, so the features are min-max scaled, and the division of the data set is as follows.
So what's the distribution amongst the languages?
Right, good question. So English is still dominant in social media, and that is represented in this data set. So about 73% of the tweets are in English. The next top 3 languages are Spanish, Chinese, and Turkish, interestingly. And they roughly figure out about 10, 5, and 3% each. And then there's a lot of other languages which have less representation and less tweets.
Right, so that's about 1,000 tweets per user in a label, right?
Yes.
So what sort of time range is that? How long of a time period do you know?
The authors of the dataset don't actually mention it, but they do mention the range in which they collected it. So they collected tweets regarding the Fukushima disaster, the nuclear meltdown. So, and they only take the first 1,000 tweets. For some people who tweet a lot, that could be maybe 1 hour. And for people who don't tweet a lot, that could be years. Right. Okay, so that's that about the dataset, and moving on. Now we can start finally talking about the implementation. So the first things first, we want to do some sort of feature selection, and instead of doing it randomly, we want to take an intelligent guess as to which features are the most important. One of the ways to do that is by ranking them according to information gain, and you see in front of you the top 20 features ranked by information gain. You might notice followers and friends already rank at the very top, specifically their ratio. Another interesting one to look at is verified. As you might remember, the verified blue check mark used to be a very strong indicator that this person was who they say they was. Unfortunately, now that is not the case because people can buy those blue check marks for like tens of dollars. Anyway, moving on. So we ranked all these features by information gain, and then we ran an experiment to decide how many features we want to take. So what you're seeing in front of you is an experiment's results where we take the first 10, the first 20, the first 100, so on. The first X features ranked on information gain and how our model performs in terms of the 4 metrics: accuracy, precision, recall, and F1. So we seem to notice that the models for our particular technique, the GAN, performs best when we just take the top 100 features. For other baseline techniques that they implemented, they need even less features. They seem to peak at 50 features only. And you might notice after 100 features, the performance seems to taper off and become a little bit worse.
Okay, so this is based on your GAN architecture?
Right, for this graph, it's just talking about GAN.
So what did you use for the hyperparameters here?
We'll talk about that in just a few slides. We actually do some hyperparameter tuning.
Okay.
What is the y-axis?
Right, so that would just be the absolute value. So everything from accuracy to F1 goes from 0 to 100.
But is it close to 50 or close
Oh,
to 90?
so it's above 90. Everything's
Oh, that's
above
90 over
Yeah.
there. That's
Yeah.
what the 90 means
Yes.
over there. Okay, okay.
Yes, I couldn't address your comments. I saw the report, but yes, that's what that is. Okay. Anyway, so that's that about the features. So we want to take the first 100 features for GANs. That is the conclusion from this graph. Now let's talk about how our GAN actually looks, how we actually train the GAN. So of course we want to train the discriminator against the generator, and we take our data set, which has both humans and bots, and the only goal for the conventional GAN is to create a discriminator that can figure out whether it's a bot or a human. It doesn't matter whether it's a sample from the data set or a sample from the generator. This might raise some questions, but essentially this is a notion of using the generator as a data augmentation technique. If you might recall, there's a bit of a class imbalance. There's about 7,000 humans and only 3,000 bots. And the generator can help us create more bot samples. And the hope is the generator creates samples which actually look like real-life bots. So for a conventional GAN, we want to train a discriminator which can detect bots. That is the hope. And of course, depending on whether the discriminator is able to correctly predict whether the sample is bot or human, the losses are calculated.
Okay, so this is kind of a non-standard conventional GAN, right? Because typically in a GAN, you have a generator and discriminator, and the discriminator is just trying to decide whether it was produced by the generator or not.
Correct. So it's a flavor of a conventional GAN, you could say.
But the generator does both bots and humans.
Yes.
So it's an unconventional conventional GAN.
Yeah, it's conventional in the sense that there's only one discriminator and one generator, and you'll see why I say this is conventional in just a couple slides. Anyway, so this is the setup, and here's what happens when we train this GAN. So what you're looking at is a loss graph. The basic idea is the red line represents the discriminator loss, and the blue line represents the generator loss. So it's immediately obvious that at the start, the generator is doing quite well, and then not so well as training goes on. There's only one way the story ends. The discriminator figures out the generator's tricks and ends up at a very minimal loss. It's able to overwhelm the generator, and the generator is never able to recover from this. And this is a problem that is called mode collapse. This is why we're seeing this sort of behavior from the discriminator and the generator. When we look at the generated samples from the generator, we see that the amount of bots that it generates per epoch as compared to humans skyrockets at around epoch 20 or so. So ideally, my assertion is that we want to generate bots and humans at almost an equal rate. And right after epoch 20, the ratio goes to about 46 bots generated for every human. And the discriminator in the GAN understands this, and it's very easy for them to say it's a bot, because 46 times out of 47, it'll be right. And that's why you see this result, where the generator starts to have higher and higher loss. So we have this issue of mode collapse, and of course we want to solve this issue. And how do we do that? We come up with a new architecture. So this is a departure from our conventional GAN model in the sense that there are many discriminators for one generator. And this dropout GAN architecture is specifically designed to get over the issue of mode collapse. So we modify our training a little bit from the conventional setup.
So why do they call it dropout GAN?
So it's called dropout because you can actually see in just this slide. So we looked at multiple discriminators training against one generator. Per epoch, it's not true that all of them will train against the generator. Only a few of them will be trained. So this is analogous to the notion of dropout in a neural network, where we disable some neurons. In a very similar fashion, we'll only train a subset of the total discriminators against this generator. And the basic idea is that the generator gets more experience. It's able to train against many discriminators per epoch and learn at a much faster rate.
So is this some hyperparameter you set as to how many discriminators or what fraction of them?
Yes, so it's called dropout, and we'll just get to it in just a couple more slides. But yes, so whether a discriminator is trained against generator in a particular epoch or no is defined by this hyperparameter called dropout. And that's basically a probability saying, okay, with what probability will this discriminator train against the generator in the particular epoch? And the basic idea is now we're not focusing on the discriminator at all. So the discriminator job in this architecture is to just make sure whether the generator sample is a believable sample. We want to make sure that the generator is, one, able to create samples which are realistic and create them in the appropriate ratio. We don't want 46 bots and 1 human per epoch. We want 1 bot and 1 human, so on and so forth. So we do that, and we set up this sort of dropout training architecture. And we'll get to the dropout just in a second. But the basic headline is, this architecture is able to get over that problem. So you'll see in the same loss curve, the discriminator, even though it gets an early win, the generator is able to fight back. And essentially, now we have a more stable training approach in the sense that the generator does not suffer from mode collapse. And just to kind of compare, this was the original loss curve on the left from our conventional GAN, where the generator just can never recover from this mode collapse problem. And after we use our dropout GAN architecture, it might seem like the loss is all over the place, but basically the discriminator and generator are able to have a competition with
So
each other.
what happens if you continue for more epochs here on the right?
It's a similar sort of story, and maybe sometimes the losses will diverge, but then they converge again eventually.
Okay, so it doesn't consistently diverge.
Yeah.
Okay.
But the objective was different for the conventional GAN, right?
Correct.
The objective was different, right?
Yes. So the basic idea is if we have a generator which can't train against a discriminator, then we can't train the discriminator to detect bots, because if we have a model that always guesses that it's a bot, then we can't really detect bots. That's why we had to take a detour to come up with this dropout GAN architecture to make a generator.
But if you try to do a conventional with a new objective, with a being generated or real, what is the loss function of this?
That is a very good question, and it's basically just about the same as this.
Oh, it is?
Yeah.
Oh, that's interesting.
But
So is that in the report?
I think it's mentioned in a line. I don't think there's a graph for it.
Yeah, maybe we should.
Yeah, we'll just revisit that. Okay, but essentially the highlight is that when we use this dropout GAN architecture, we're able to come up with a generator that doesn't suffer from mode collapse. Finally, the slide everyone's been waiting for, the hyperparameters. So of course we tune the hyperparameters, and I want to draw your attention to dropout rate. So dropout, if you remember, is a probability with which we decide whether a discriminator trains against a generator in the dropout GAN architecture. Very interestingly, it seems that if we just set the probability to 0.5, so if you just flip a coin and decide that, okay, this discriminator is training against this generator, it seems like you get the best results in bot detection. The other sort of interesting hyperparameters, I guess, would be the number of epochs. It seems like 50 is the optimal amount to train our GAN for bot detection purposes.
So what would a dropout rate of 1 mean?
So a dropout rate of 1 would mean that all of the discriminators train against the generator every epoch. There is no possibility where one.
What about 0?
Yeah, a 0 would be where no discriminators train at all. That's sort of a meaningless epoch, but you could technically do that. Right.
So this is continuous also, script?
Yeah, you could technically vary it by like different amounts, so it doesn't have to be 0.1, 0.2, it just be any function you want. So that's that about the hyperparameters. We do a basic grid search to determine the best result. So of course we try all sorts of combinations to figure out which hyperparameters are optimal. And now we come to this notion where we mix and match the discriminators and generators between the two architectures. So if you remember, our original goal is to come up with a model that can detect bots well. So we take the best performing discriminator from our original GAN setup and we call it D star. We have a model that shows promise towards bot detection. This is called D star from our original setup. And now we have a generator from our dropout GAN architecture, which can hold itself, doesn't suffer from mode collapse. So we call that generator G star. So there's two different discriminators and generators from two different architectures that we will now train against each other. And now, obviously, now that we have a generator that can train against a discriminator, now we can come back to our original problem of bot detection and now train these two against each other. So we do exactly that, and what happens first is we want to figure out what's the best way to train this G star. So in this experiment, the basic idea is we're experimenting with a dropout GAN architecture. We're figuring out how many discriminators do you need. Is it only one? Is it only two? We find that as soon as you do 5 discriminators against one generator, remember the dropout of 0.5, we're able to generate convincing samples. So remember, the goal for the discriminator here is whether the sample is real or fake. So as soon as we do about 5 discriminators against one generator with a dropout of 0.5, we see that now the discriminator is not able to tell whether the sample is real or fake. And you might notice that the loss varies a little bit, but eventually just keeps on increasing if we increase the number of discriminators. So we now have this magic number that, okay, use 5 discriminators and your dropout GAN. Now, let's go back to our conventional GAN, and now we can finally get to the issue of bot detection. Now we're measuring our D star performance. Remember, we're talking about whether a particular sample is a bot or not. And we see that when we train a D star against a G star with 5 discriminators, the accuracy seems to be the most optimal. So it seems like for both of these cases, 5 is the magic number for a dropout GAN. We also want to measure how much we can augment this data. So what happens if we don't use the augmented data at all from the generator, versus what happens if we only train on the synthetic data from the generator? What you'll notice is that, well, there's not a whole lot of difference, because if you might notice, the graph starts from 90.42, and this is about accuracy. But we do notice a slight difference, so there's about a few decimals worth of difference, and 0.2 seems to be the magic number. So if we have about 80% real data and 20% synthetic data, then our discriminator performs the best on bot detection. And now for the main slide, how good can we predict bots? So the first thing we want to do is compare against some other famous techniques. So we first trained a KNN model, an SVM, an MLP, and a random forest classifier. And you can see the metrics for them in this table. And you might notice that our technique performs the best at about 99.3% accuracy and an F1 score of 99. On the right, you'll see the comparison against previous work. So these are techniques that have been applied to the same data set on the same problem. So you might notice again that our technique is the best, although by a narrow margin. MSGS comes pretty close at about 96.5% accuracy and about 96% efficacy.
So what is MSGS? What are they doing?
So essentially, MSGS wants to create an ensemble of different graph neural networks to basically predict whether it's a bot or not. They look at slightly different data than we do. Remember, we're only looking at the tweet features. We're not
So
really
it's the same data set, different features.
correct.
Yeah.
So all of these techniques on the right, you'll notice, are actually graph-based techniques in the sense that they look at edge features or node features, and the only thing we're actually looking at is just like the features about the account, like the account data and everything else that we showed.
So was there any previous work where they did not use graph techniques?
There was. All of these techniques were also tested in the same.
Previous work ones.
Right. So there was one that was basically using a variation of Ada Boost, but it wasn't as good as these.
Variation of what?
Ada Boost.
Boost.
Yeah, boosting essentially, so like XG Boost or.
So you don't use graphs, right? You just take the features
Correct.
that you get from the bird and
Yes.
the other features, and this is what you have.
Yes.
That's your input.
Yes, that's it.
And that's your okay.
Yeah. So it seems like we don't need to use.
Text.
Yeah, exactly. But yeah, essentially the headline is that this technique is really effective and we can predict whether a user is a bot or not with about 99% confidence.
Can I just go back for a second?
Sure.
So compared to previous work, how did you have a feel for the testing and training time and how it compares to your approach?
Unfortunately, no, because we did not reproduce these on the right. It would be too time consuming to implement them from scratch. Unfortunately, most of them do not share code with us, so there's not an easy way to reproduce those results.
Okay.
So how about the ones on the left? How does the dropout gain compare to the other standard techniques, timing ones?
Oh yeah, so the dropout GAN is a little bit slow because obviously it's a little bit more complex. So to give you a ballpark estimate, the slowest of these techniques was about 30 seconds, and the dropout GAN takes maybe about 1 minute to train to completion.
With all the data set.
Yes. So it's the same amount of data on all these techniques, just to kind of keep the comparison relevant. Okay, moving on. So just to put into perspective the numbers across both the previous work and the baseline techniques, essentially we're wrong 3 times less than the next best technique and about 15 times less than the baseline technique. And to really drive home why that matters, we came up with a metric called impact. Essentially, impact is just the product of the number of followers and the number of posts for a given account. And of course, it's normalized across all users. The basic idea is if we deploy any sort of machine learning model to automatically ban an account that's suspected to be a bot, there is a negative aspect to it. Let's say tomorrow our model bans the President of the United States, and your users will not be very happy with such a scenario. So to measure the impact of misclassifying both bots as humans and humans as bots, we came up with this metric called impact. And we also want to figure out how well the technique does. So remember, impact is on a per account basis. Impact mitigation is basically summing it all up. And in this case, it's a positive impact mitigation if you correctly classify it, and you subtract it if, of course, you misclassify it. And now let's look at how our techniques performed in terms of this new metric that we defined. So if you remember that KNN was roughly around 83% accuracy, so it's not doing too bad in terms of how many misclassifications it did. So it seems like the accounts it's missing are not that impactful. Maybe they're new, maybe they don't post a lot, so it's not too bad, the accounts it's missing. SVM and MLP, you might notice, even though they're about 5% better in terms of F1, they have not much of a jump in terms of impact. So it seems like it's,
I'm missing something. Why is it different? Is it not the number of followers, number of posts the same across them? Or is it for human and bots?
I didn't get your question.
So why are all these different? Because if you take the impact, the number of followers and number of posts should be the same data set. Is it
It's different accounts. So obviously it could be a new account which has no posts or followers, or it could be a very popular account.
But do you take into account only the bots or the humans?
Oh no, this is across the whole data set, bots and humans. At the end of the day, we want to basically predict whether it's a bot or a human across the whole population, right? It doesn't make sense for us to only look at bots or humans, because we're basically trying to measure the impact of what happens if you deploy this model in the real world on a particular social media.
Yeah, but the formula that you have is when you have your data set, it's independent of the machine learning approach you're using.
Yes.
It should be independent, right?
Yeah, it is.
It's the same value, but you have
So you go back to so you're talking about the formula.
the formula, it's independent from the machine learning, it's from the data sets, it's like statistics.
Right, but it depends on which ones you classify as which, right?
Oh, you do it after you classify.
I mean, this is per.
This is per account, yes.
Per account, right?
Per account, right. But it doesn't
So
show
if-
if it's.
So if you declare an account a bot, then there's an impact to doing it, right?
Right, so coming back.
Where does it show that there is no, it
I
doesn't
think it's
depend?
measuring this, the impact of a single account.
Yeah, the impact, but the impact is, it doesn't matter if it's a human or a bot, it's the same.
Right, so basically what we're trying to measure is the problem that happens with misclassifying a human as a bot or a bot as a human. So if you ban a human account saying that it's a bot,
Right.
then there's a problem.
Right.
And of course, if you don't ban a bot account thinking that it's a human, there's still a problem.
But, so that's not for all, that's what I mean, it's not for all users, the impact that you have.
So it's counted for both. So basically, if you correctly classify it, you add it to this impact mitigation.
Okay.
And if you misclassify it, you just subtract the impact.
Okay, that's
Well,
what I'm saying,
yes.
right.
Right.
Because when you do it, it should be the same
Right,
across
right,
it,
right. Okay, so coming back to the notion of impact mitigation. So the point I was trying to make was SVM and MLP seem to miss more substantial either bots or humans. So either they're misclassifying too many humans as bots or vice versa. Of course, our technique seems to perform the best, so we're still at 0.98. You remember that our F1 score is 99, so it seems to make sense that we're not missing the most important misclassifications, essentially. We also wanted to figure out how quickly we can detect whether a user is a bot or not. So we want to measure the account age versus the performance of various techniques. So the basic idea is, in an ideal world, as soon as you look at a freshly minted account, the second it's created, you should be able to predict whether it's a bot or a human. Of course, that's not possible, and that's what we see from our results. So what we do is basically binning into percentiles on account age. So 0th percentile would be the youngest account in our whole data set, 100th percentile would be the oldest. And what we basically see when we go 1 percentile bin at a time, obviously across time our accuracies improve. But the basic inflection point seems to be at exactly around 30 or 35 percentile. That is when we see the biggest jump for all of the techniques.
So is this based on the age, or is it just based on the fraction of those 100 or 1,000 tweets?
So this is just on the age, only on the account age, and they might have different amounts of activity, or activity in terms of followers or posts.
So what's the data set like though? Do you tend to be a number of old not accounts, or do bosses?
So interestingly, I'm not sure if the data set authors wanted to do it that way, but there seems to be almost an equal number of accounts in each percentile. But yeah, that's beyond our hands because the data set was given to us.
So why is it that you're getting better results? Just because there's more data to go with?
Right, so the notion is, of course, if you don't have any tweets to work with, then your tweet features are not going to make a whole lot of sense, right? If you have nothing to look at. If you can make intelligent predictions about, okay, this account is friends with 20 other bot accounts, then you have a very clear argument for saying that this account is a bot or not. But if it doesn't have any friends, if it doesn't have any posts, then you can't really tell either way, right? You need some sort of data to work with to make a prediction. That's the basic idea. And so we see that at around 30 to 40, we see a big jump in performance. and then it tapers out. At that point, we have enough data to work with to make a prediction. And it doesn't really change, like adding on more information about followers or posts or whatever it is, doesn't really help our case. Lastly, the most interesting thing that we wanted to explore was which features are being used by the generator to actually make our discriminator believe that this is a real life sample. And basically what I've counted is the number of misclassifications by the discriminator. Remember, the task on this is whether the sample is real or fake. And there was only 71 misclassifications in this particular case out of 10,000. Right, and basically when I say that 71 misclassifications had a followers count that was close to a real life sample, I essentially say that for this particular sample, the followers count was within 5% plus or minus of the average of this feature for a real sample. So what we really see is that our discriminator is really dependent on followers count, friends count, and favorites count, also verified, and so on and so forth, to really distinguish between bots and humans. And if you might remember, this seems to track because these are also the features which have the most information gain. So it sort of makes sense that the discriminator will be reliant on these few features to make actually believe that this is a real sample. So if you are a bot author, then you might want to look at these particular features to think about how you can fool a detection technique such as this. Wrapping things up, so essentially the crux of this work was to do social media bot detection. So in particular, how GANs can be used for that. We also looked at how a dropout GAN approach can work to prevent mode collapse from occurring. We explored a few other factors that affect the discriminator performance, like hyperparameter tuning, so on and so forth. We proposed a new metric called impact to measure the consequences of misclassification, and we examined which features the generator actually relies on to confound the discriminator. In terms of future work, we can, of course, extend this approach to datasets beyond Twitter accounts. So for this particular problem, we used a dataset that was only about Twitter. Of course, we can extend it to other social media platforms. We can experiment with different sorts of GAN layers. So we can use LSTM layers or convolutional layers instead of just linear layers. We can also experiment to actually come up with a bot that actually confounds this approach consistently based on the findings about the features that we looked at. And we can, of course, repeat these experiments with other techniques like the previous work to have a more complete comparison. And that is that to me. So, yeah.
So I'm kind of curious about this third point here.
Right.
So that sounds like a really interesting problem. So could you say a little more about that? Could you use GANs to do something like that? Could you produce some automated techniques that would help you there?
Well, you're almost right on the money because we already have a generator that's producing like an account. You're basically able to reverse engineer that if you want to have an account that evades this technique, then you should have these many followers, these many friends, the ratio should be this much. So you basically have the blueprint ready to basically evade this sort of technique. So it would be a very interesting exercise to create a computer program or a bot that would mimic all of these attributes.
Right,
And
so
then
you could just create fake accounts. Right?
Exactly.
And see how
Exactly.
hard they are to classify.
Right. But yeah, that's all I have to talk, so I got any questions. Yes.
Have you looked into the case where, let's say, an account is created by a human, but occasionally a bot posts tweets?
No, so we don't have this notion of mixed use accounts where it's both humans and bots working on the same thing. We're doing a binary classification of it. More questions? Yes.
Did you ever think about using like the impact statistic that you come up with in the training? Like if it says like, oh, this is a bot, then you calculate its impact and then do further classification after.
So you mean like use the impact as like a surrogate loss function, you mean?
Kinda like
So
that.
that's actually a good question. So this impact is sort of like a weighted accuracy in some
Right,
sense, right?
right.
So it makes it, you want to get rid of the ones that really count, count the most.
Yeah.
Right,
So
right.
could you work that into the loss function or something?
That would require some tweaking, mostly in terms of implementation, but I'm sure it's possible to do. I haven't done it for this, of course, but yeah, it could be done. Right, one more question?
Given like when you had the time, like that 40 percentile, about 30 percentiles, like how much time, how long do those accounts exist? Do you know?
Right, so unfortunately we don't because the data was already pre-scaled for us. So in terms of the account age, we're only seeing numbers between 0 and 1 essentially.
Got it.
But I could make an educated guess because all of this tweet data was from around 2011. At that point, the oldest accounts were about 5 years old. So if it so happens, then the oldest account could be technically 5 years old, the newest one could be 0 years old. But of course, that's just one theory. It might not actually be distributed that way.
So it might take you a year to be able to detect the bot account?
Right, you have to play the long game to avoid detection from this sort of technique. More questions?
Do you have intuition why the mod collapse happened with the traditional GAN?
I think it's something to do with the class imbalance, but just the other way. I think that basically the motivation of the generator is to fool the discriminator, and I think what happened was the discriminator initially focuses on the bigger class, which is humans, right? So as soon as a generator, first time it shows a bot, it has some initial success. So it kind of becomes over enthusiastic about that idea and only starts generating bots. And the discriminator then catches on very quickly, and then the generator becomes recovered, basically. That is my intuition, but it would require more experimentation to prove that.
So just within the standard GAN architecture, couldn't you like retrain the generator multiple times before it for each discriminator or vice versa, make sure one doesn't get stronger than the other?
Yeah.
Instead of getting multiple discriminators or whatever.
We did try that initially, but it wasn't working for whatever reason. So I did try tweaking around with the learning rate between the generator and discriminator, trying to make sure that the generator tries to learn faster than the discriminator. Other experiments on how the discriminator and generator actually are in terms of architecture, but nothing seemed to work. So
Did you randomize the data set and try to put the bots first and then the real?
yeah. So we always do a random sampling. We shuffle the indices every time, right? Yeah.
And then what does the feature of the tweets do? Because you don't have them as feature. You did take feature of the tweets themselves, right?
Right. Right.
Right? They are not important for the information gain and stuff?
It seems not. It seems that these characteristics seem to matter more, and the tweet features themselves are not that helpful overall.
Did you try also a combination of impact factors, like because you say that the followers, the friends count, the favorites count is substantial more important than the others?
Unfortunately, no. But of course, we could always extend that work and try different sorts of features to define our impact metric.
And what was the most difficult with the GAN training? Those GANs are notoriously
What's that?
Right. So.
The GANs are notoriously difficult to train and convert and all this stuff.
Right. So obviously, all of the classic problems and conversions not happening and all of that. So it was mostly just an initial hump in difficulty with just trying to get some sort of discriminator that shows promise. But of course, once we sort of realized that there's this dropout GAN architecture that could potentially work and we saw really strong results, then it was a little bit easier to make progress and then continue on and on. But the initial setup, just to kind of make sure that your GAN should work in theory, that was the hardest bit, essentially.
And you did avoid graphs, I see.
Yes, I tried my very best to avoid using any sort of graphical information.
Okay, any other questions? Okay, if not, if you're here for my class, be sure to sign up as you leave, and you can pick up a cookie or something on your way out, or we need to kick everybody out at this point.
Thank you.